Okay. Today the topic of the lecture would be basics of aero and hydrodynamics. So we are going to stop discussing the gases and liquids which are held in place, so which don't exhibit any kind of a macroscopic movement, and we are going to slightly delve into the subject of flows of liquids and gases. So in addition to some thermodynamic phenomena which happen due to the microscopic motion of molecules, we would also discuss aspects which arise if there is also some macroscopic motion present in the system. So I think so given the appropriate conditions, like the velocity of the liquid of gas when it's not too high, and then the liquid exhibits so-called laminar flow, and the laminar flow means that you can separate all of the flowing portions of your fluid into so-called streamlines. So in each the streamline you can consider it as a tube which consists of gas or a liquid, and the different tubes do not mix. So indeed the motion of all of the particles seems as though they can be separated into many different threads which do not mix with each other. So of course this is one of the most simplest types of the flow, because also there is a counterexample. The flow can be pretty much different, and that another type of the flow is called turbulent flow, when you have a chaotic and complex movement of fluid in the liquid, or in the gas. So this one is the most simple, and we are going to make it even more simple by assuming that the flow is stationary. Stationary in this context means that all of the velocities at any point of the fluid are functions constant in time. So as the time goes on, nothing changes in the distribution of velocities. Okay, so here I have written this condition as that the partial derivative of velocity over time is 0. Okay, now we are going to establish some important laws which govern the flow of the fluid. One of the I think most obvious one is the continuity equation. So if you don't have any kind of disruptions or cavitation when there are some parts of volume which are not filled with the fluid, then you can assume that for any closed volume, so the most basic condition is that if you take any closed volume, then the amount of fluid inside that closed volume remains constant, so it doesn't change with time. So in terms of dynamics, that means that the amount of liquid which flows into the closed volume should be exactly equal to the amount of fluid which outflows from that closed volume. And this condition can be, I think, written mathematically. So if you consider, for example, kind of a streamline, then you can associate like a cross-sectional area of that streamline. And that cross-sectional area is not a scalar but vector value, because I think it was discussed during your calculus course that if you have any kind of a surface, then you can ascribe a vector which is perpendicular to the surface and whose absolute value is equal to the area of the surface. So that would be a so-called element of the surface. The direction of that element of the surface depends on which side you consider to be like the inner side and which side is considered to be the outer side. Of course, let's say, for example, that something which is below this surface, okay, this side is considered to be like inner side over some side wall. Then here goes the outer side, so that this is something which is located outside of the closed volume, which is formed by the whole surface, so not by an element, but the whole surface. So then you take this direction of that vector to be directed to the outside of the surface. So in that case, the flow of the fluid through that element of surface is given. So this is the volume of the fluid per unit of time. So I'm going to write that this is dV over dt is given by this expression. So I need to calculate a scalar product of the velocity and the element of the surface, and that would give me yes, the amount of the volume of the fluid which flows through the surface per unit of time. And if the density of my fluid remains constant, which is approximately valid for any liquid, then I can assume that if I take the inflow equals to the outflow, so let's say this is V in and this is V out. So if I write that inflow equals to the outflow, and since I consider the closed volume whose side walls are going along along the streamlines, that means that there is no flow of liquid through the side walls of my closed surface. So that means that all in all, I need to write that the product of V times ds should remain constant along the streamline. And that's assuming that the density is constant. But if I consider gas, and for example, if I assume that, for example, temperature of the gas is different at different parts of my flow, and also the pressure of the gas may change at different parts of my flow, then I need to slightly modify this condition. I need also to add density of my fluid into this equation. So in this way, this expression would give me mass per unit of time which flows through the surface. So no longer like I can say that the volume coming in should be equal to the volume coming out. To demand that the amount of the fluid remains constant, I need to demand that the mass of the fluid which goes into the closed volume should be equal to the mass of the fluid which goes out of the closed volume. So that is for when the density is not constant. Okay, so that is for the continuity equation, but we should also have another kind of equation. That equation should represent, for example, energy conservation law. And in the case of hydro and aerodynamics, it's typically assumed that the so-called Bernoulli equation does the job. So Bernoulli equation represents the energy conservation law in my fluid. Well, I have seen some statements that is not exactly true. So actually, Bernoulli equation describes something more complicated than just energy conservation. But for the simple case I'm going to discuss now, these nuances would not be of any matter. So Bernoulli equation would indeed be the energy conservation law. So let's first derive, for simplicity, the Bernoulli equation for the liquid. So once again, we are going to consider some volume which is occupied by a number of streamlines. And so I'm going to consider a streamline here. And let me fix it slightly. So I'm going to consider a streamline, and I'm going to, since I'm considering a streamline, that means that I consider a stationary flow of the liquid, or not a stationary, but laminar flow of the liquid, but moreover, I also consider a stationary flow here. You will see how it really matters in case of Bernoulli equation. So now I assume that I choose some surface like, let's say, let me denote some points here. Let it be points A, B, C, and D. So that's a projection, but of course, when I say A, B, I don't mean the line, I mean the surface. So in here, if I consider the surfaces, so let's assume that first I look at my fluid at some moment of time t equals to 0. And I have surfaces AB and CD, and I consider the fluid which is located in between these two surfaces. So in between these two surfaces, so I consider the volume ABCD. And now what I'm going to look at is that with the passage of time, my liquid would shift from its initial position. So that means that after some time has passed, all of my fluid would be located in between, now again, in between the surfaces A prime, B prime, and C prime, D prime. So instead of the volume A, B, C, D, all of my fluid shifts to the volume A prime, B prime, C prime, D prime. So I focus on the same molecules of fluid. So they initially have been here, but due to the motion in the flow, they have been shifted. So now let's write the energy conservation law for all of that. And for now, let's assume that the density of this fluid remains constant. So let's assume that we are dealing with a liquid. So that's a constant. Okay. And now also let's assume that temperature here is also constant. So let's give some more approximations. So let's consider, I think, the most simple case. And also we need to assume that there is no friction in the system. So in this case, in textbooks, it is said that we deal with the so-called ideal liquid. Ideal liquid, in which, for example, viscosity is 0. So there is no friction in between this streamline and other streamlines which are located close by. Okay, so there is no energy loss in my system. So then I can write the following equation. The equation for the conservation of energy is as follows, that the work done on my liquid in this process from t equal to 0 to t equal to tau, the work done should be equal to the change in the energy of my liquid, and the change in the energy includes both the change of the kinetic energy, so delta K, plus a change in the potential energy. So let's say, for example, we also have gravity in our problem. So then there would be potential energy too. Okay, now let's calculate both sides of this equation. And for this, we need also to give some additional assumptions. We need to assume that the streamline which we consider is so small that the pressure everywhere here is constant, and the pressure everywhere on this surface also remains constant. Moreover, I assume that not only the pressure along the surface AB, but also the pressure at the surface A prime, B prime are also constant. So that pressure I would call the pressure P1. And also I assume that the pressure on the surface CD and the pressure on the surface C prime, D prime is P2. These assumptions are not unrealistic, they're actually quite realistic, but it requires you to consider a very small streamline and a very small displacement. So that means that this amount of time tau here, which has passed from the initial moment of time, is very small. So that the shift of that fluid is very small, so the pressure hasn't been able to change during the shift. That allows me to calculate the work done on my fluid quite simply. I just need to, let's say I have pressure acting from here, P1, and pressure acting from here, P2. So that would be external pressure. So as I consider the portion of fluid in between these two surfaces, that means that external pressure pushes from the outside into to the inside. So I write, and here I write for the work done, P1 times delta V1 minus P2 delta V2, where delta V1 is the volume change in here, and delta V2 is the volume change here, and actually these two volumes are equal. So I can actually replace them by some delta V, but let's write first delta V1, delta V2. I think that will be dealt with afterwards. So now about the change in the kinetic energy. The kinetic, yeah? Yeah, they are not the same. So the pressure is the same in this part of the fluid and in this part of the fluid, but they are different between this part and this part. So I can write that P1 is not equal to P2. So I assume that these two parts of the fluid are specially separated. So while there is almost no separation in space, so while this portion is located in a very closed or in a very small amount of space, and this one is too located in a small amount of space, the separation in between these two portions of fluid can be large. So that means that the whole pressure can change from one value to different value, and the change can be quite significant, so it can be large. Okay, so with these assumptions, I am able to calculate work quite easily. So it is done in the same manner as I have done the work done by the gas. So I calculate the pressure times the change in the volume, and again here, pressure times change in the volume. But in here, negative work because my surface goes like counter to the pressure, and in here, the surface goes along the external pressure. That's why in here the work is positive, but in here it's negative. So well, all in all, that gives me this. And to calculate the change in the kinetic energy, so if you don't need this, please tell me if you don't need this anymore. You don't need. Okay, so if I want to calculate the change in the kinetic energy, then literally what I'm going to calculate is, first of all, I need to calculate the kinetic energy in the volume A, B, C, D. initial volume occupied by the liquid, or yes, by the liquid. And okay, it would be minus initial kinetic energy and plus final kinetic energy. So to calculate the increment, I need to subtract the initial value from the final value. So in the final value would be kinetic energy in the volume A prime, B prime, C prime, D prime. But so that means that I need to know the kinetic energy in the whole of this volume, but to calculate that is quite difficult because I have also this large volume here, and I even might not know the distribution of velocities inside here. So it looks like it would be quite difficult to calculate, but it turns out that actually the kinetic energy inside the volume A, B, C, D can be presented as sum of the kinetic energy in the volume A, B, B prime, A prime. So in this small volume, delta V1, and plus kinetic energy in a very large volume, now it goes A prime, B prime, C, D. And I can do the similar procedure for the kinetic energy in between A prime, B prime, and C prime, D prime, and that would give me kinetic energy in C, D, C prime, D prime, plus kinetic energy in a very small volume C, D, D prime, C prime. So what I notice here, that both the initial and the final kinetic energy contain the kinetic energy in this large part. So when I calculate the change in the kinetic energy in this large part is being cancelled out. So I can cancel out this A prime, A prime, B prime, C, D. Plus CD, D prime, C prime. So these two can be cancelled out. And what remains here is kinetic energy in the volume delta V2 minus kinetic energy in the volume delta V1. And again, since both of these volumes are considered very small, then what I can actually write here that it is actually equal to density multiplied by V2 squared over 2 times delta V2. So density times the volume would give you mass, and mass times velocity squared over 2 would give you kinetic energy. And minus the same expression for the first volume, minus rho V1 squared over 2 times delta V1. The same can be written about the potential energy. I'm not going to reproduce like this argument here. I'm going to write from this part. So the potential energy in the volume delta V2 minus potential energy in the volume delta V1. And that would give me rho G H2 times delta V2 minus rho G H1 times delta V1. Okay, and also I take into account that delta V2 actually equals to delta V1, which follows from the continuity equation. And the fact that the density is the same. So altogether, after I plug in here, I can write that this is equal to rho V2 squared over 2 plus rho GH2 minus rho v square v1 square over 2 plus rho gh1, and everything multiplied by delta v. So now you see where it follows. I can combine quantities related to the first portion of volume and the second portion of volume. And after I combine them all together, I would get the following equality, which says that P1 plus rho V1 squared over 2 plus rho GH1 equals to P2 plus rho V2 squared over 2 plus rho GH2. So if I go along the streamline, even if I go far apart from the initial point, then this quantity remains constant. And this is how sometimes Bernoulli equation is written. P plus rho V squared over 2 plus rho GH is constant. Okay, let's now have a 3-minute break. So I'm going to show you the slide probably which you have missed, because I was able to come here slightly earlier than I have expected, but I have started exactly 15 minutes after the official start of the class. So in the very first slide, I have introduced the concept of laminar flow, in which all of the velocities are are distributed in such a way that they form streamlines which do not mix. Then I have introduced the concept of the stationary flow, which I extensively use in my derivation of Bernoulli's equation. Bernoulli equation is valid only for the stationary flow, because it heavily relies on the argument that the energy in that very large part in between these 2 points I have considered remains constant. So, okay, and let me show, probably there is something here. Oops. Yeah. After that, I have discussed continuity equation. Okay. Now 3 minutes break. After that, we continue. Okay. In the following part of the lecture, we are going to rederive the Bernoulli's equation in a more complicated case. So we are going now to include the possibility of temperature changes and the possibility of the changes in the density, since we aim for a new equation to describe not only the flow of the liquid, but also the flow of gas. But the other assumptions will remain the same. So I'm going, again, to assume that my flow is stationary and my flow is laminar. So let me start again from the very same picture as I had previously. So let's assume that we have some sort of the flow. And we look at the amount of liquid between these two surfaces, A, B, and C, D. Wait for a small moment of time to pass and see that these surfaces have been shifted by the motion of the gas. Now once again, I have two portions here. One portion is being subtracted and its volume is delta V1. And one portion is being added here, is delta V2. So now I'm going to do the same stuff again, but previously when I have written the energy conservation law, it was the energy conservation law for the mechanical energy. So in my formulation, I had kinetic and potential energy. But in here, I should instead write thermodynamic energy conservation law. That is the first law of thermodynamics. So that would give me that delta V, the amount of work done on this portion of gas, should be equal to the change in the internal energy of my gas plus, once again, changes in kinetic and potential energy. Okay, so now when I deal with gas, I can no longer take that delta V1 equals to delta V2. So that's wrong. So I cannot use that anymore. What I can use is that the amount of gas in these volumes is equal. Delta nu1 equals to delta nu2. So I will be aiming to express everything here in terms of, in terms of number of moles of gas in any kind of volume. Everything else remains the same. Like, for example, delta U is actually equal to the internal energy in the small volume delta V2 minus internal energy in the small volume delta V1. And again, this is the consequence of the stationary flow. So we have stationary flow. That's why the energy between these two surfaces doesn't change. All the changes happen only in these very small volumes, to the left and to the right of the large volume here. Again, the same for the kinetic energy, K at delta V2 minus K at delta V1. And the same for the potential energy. Well, actually, I can even, I guess, omit the part which writes all of this in terms of some speeds and other. I can just write that this delta V is again equal to P1 delta V1 plus P2 delta V2. And since I want to save some space on the blackboard for the derivation, I'm going to combine all of the terms related to each of the small volumes in each of the respective sides of the equation. So I'm going to write that P1 delta V1 plus U delta V1 plus K delta V1 plus potential energy in delta V1 equals to all of the same, but at the point number 2. So once again, I can write that P delta V plus U plus K plus P is constant. So now I'm not going to carry all of the terms related to the second volume, so I can say that in any small part of volume which has the same amount of gas in moles, everything written here will be the same. Okay, now let's look at this part. The question to the audience, what is this? U plus P delta V. No. The hint is that it is one of the 4 thermodynamic potentials. Remember one of them. Internal energy, Gibbs energy, free energy, and enthalpy. And which one is this? This is enthalpy. Okay, so that's correct. So I can write that H plus K plus P is constant. Okay, for the same amount of gas. Okay, since all of these quantities are additive, so if I increase the amount of gas by a factor of 2, then all of them increase by a factor of 2. I think we can write all of them with respect to 1 mole of the gas. So for example, enthalpy for 1 mole of the gas, kinetic energy for 1 mole of the gas, and so on and so forth. So enthalpy for 1 mole of the gas would be something like, in case of real gas, it is some quantity H. I don't know which one, but there is some function. In case of kinetic energy, I can write that the mass of 1 mole of the gas is mu. So the speed is v, so mu v squared over 2. And potential energy for 1 mole of the gas is mu times g times h. Oops, now I have a trouble because h here is the elevation. So the elevation and also h here is enthalpy. So I can write as hm, molar enthalpy. Molar enthalpy plus molar kinetic energy plus molar potential energy is constant in the streamline. And when you consider the gas which is close to being ideal, then you can replace the molar enthalpy with Cp times T, where Cp is molar heat capacity at the constant pressure. So that would give you something like Bernoulli equation for the ideal gas. Oops, and I have forgot, oh yes, pressure is inside here. So instead of pressure, like what we had in Bernoulli equation, we now have molar enthalpy. And you know, we have previously discussed one of the processes which conserves enthalpy. Do you remember this process? It was discussed exactly during the previous lecture about real gases. I have said even that there is some sort of inversion temperature involved with this process, and also that this process is a core part of the industrial processes for liquidization or the obtaining cryogenic gases. Joule-Thomson process or gas throttling. So it obeys exactly the same laws. Joule-Thomson process or gas throttling. So let's have a short reminder here. So in here I had some porous substance here, but the flow of the gas to the left of that porous separator and to the right of the porous separator is laminar. So I can use the same law here, and everything is kept in the stationary conditions. So that means that I can use the same laws for this exact process. But I neglect in my Joule-Thomson process the kinetic energy, because mostly this molar enthalpy in Joule-Thomson process, molar enthalpy of the gas Cp times T, but well, when I have the real gas, that is okay, H molar is much larger than kinetic energies. Is much larger than kinetic energies. So in this case, I can just write that I can discard the second term, and also the change of the potential energy is also very small compared to the molar enthalpy. So in here, Hm is much larger also than mu gh. So some changes in the height and between different parts of my setup. So and that means that in Joule-Thomson process I can write that H1 equals to H2. So this is the isoenthalpic process. Have you had the lab about the laboratory work about the Joule-Thomson process and properties of real gas? So I think you would have it, and if you look closely into theoretical description, At first it contains all of these terms, but then some estimations are being made which show that these properties are actually valid, so I can discard them. So during the previous lecture, I haven't delved too much into the subject of Joule-Thomson process. I have simply derived the equality of enthalpy. But actually, yes, so since the velocity of the gas may change to the left and to the right, and probably the velocity to the right is larger than to the left, so there is actually some slight decrease in the enthalpy, but it is so small that it cannot be seen in any kind of a characteristic. Good. And once again, let's establish some sort of connections with the previous lecture. I have said that Joule-Thomson process is irreversible. So that means that if I consider, for example, the entropy in this process, then I might discover that entropy actually increases. So let's check whether it's correct or not. So in here, let's write, so we can write that the change in the enthalpy is 0. Yes, dH equals to 0. And now let's remember the differential for the enthalpy. Anyone to volunteer to say me the differential for the enthalpy? As you see, I use this differential so much that is a hint for you that you should remember them. And also remember the thermodynamic potentials. And also there is some stuff to remember for people who study, who major in biotechnology. I will say them separately for those of you who major in biotechnology, because during the next lecture there would be some stuff to remember for people who study in aerospace engineering. But previously there was some important stuff for biotechnology, and actually this stuff is so important that actually your dean has proposed for the general physics department to have a 2-semester thermodynamic course for you. To go into further details of that stuff which I'm going to explain. Okay, so dH. There are different approaches to finding the differential. One of them is that you have some kind of a paper in which it's written and you can look at C. If you don't remember, let's say for example, you're in exam and you have forgotten the paper, and for example, I forbid you from asking your relatives or friends and other people about the answer, or other students of MIPT, then you can derive it yourself. Well, at least you need to remember that enthalpy is internal energy plus PV. Okay, so now for the, so if you know du, then you can actually calculate somehow dH. So first of all, you need to understand how to calculate du. And the question is how to calculate du. This is something related to the first law of thermodynamics. So you can write that actually that du is delta Q minus P dV. So this is work done. This is the amount of heat supplied to the gas. Okay, and now you remember that delta Q can be somehow related to entropy according to the second law of thermodynamics. So that gives you TdS minus PdV. TdS minus PdV. So now I'm going to plug this into that equation. So if I have H equal to du plus PV, so I can write that this is d of u plus PV. So now I'm having some sort of a fun calculus exercise about differentials. I don't know whether you are familiar with working with these differentials, but well, the rules for working with differentials are pretty much the same as the rules for working with derivatives. So differential of the sum of two terms is equal to the sum of differentials of different terms. Okay, so now I have something new here, the differential of the product. So I need to somehow write differential of the product. And again, I'm going to use the multiplication rule for the derivatives for calculating this dPV. So first I'm going to replace this du with this nice expression that we have derived previously. And then I apply the multiplication rule to this differential. So multiplication rule says that if you want to calculate the derivative of the product, then you first need to calculate derivative of the first factor, and then they calculate the derivative of the second factor, and then combine them in such a way that, let's say, uv prime is u prime v plus uv prime. For differentials, it's quite the same. So to calculate the differential of uv, you need to calculate differential of u and multiply it by v plus u multiplied by differential of v. So all of the rules which you are familiar with for derivatives, they, without any changes, apply to differentials. So in here I have dpv, so that gives me p dv plus v dp. p dv and p dv is cancelled out, so I can write that this is t ds plus v dp. Okay. So in my isenthalpic process, dH equals to 0, so I can write that TdS plus VdP is 0. But at the same time, I have said that Joule-Thomson process is irreversible. So that means, okay, so I can push my gas when the pressure P1 is larger than pressure P2. But not the otherwise, not the other way. So if I have a let's say a movie which shows me how Joule-Thomson process works, then if I reverse this movie, then it would look like as if I have applied small pressure from this side and have applied large pressure from this side, but for some reason gas flows from here to here. This is, well, this is impossible. So that means that in my Joule-Thomson process, dP is less than 0. That actually means that VdP is also less than 0, but the whole sum is 0. That means that this part of the sum should be positive in order to compensate for the negative second term. This one should be positive. So in my Joule-Thomson process, ds is greater than 0. S should be expected from any irreversible process. Any irreversible process. Okay, now let me see how much time of the lecture I have. Well, I have actually quite much. So I can slightly discuss this stuff for you biotechnologists and biochemists. So in the lectures related to phase transitions, I have derived the following main important rule for equilibrium between different phases. So I should write that chemical potential of the phase 1 is equal to the chemical potential of the phase 2. I haven't given you any explanation about why this quantity mu is called chemical potential. So have you wondered why this is called chemical potential while I apply it only to phase transitions? There is nothing chemical in phase transitions. But there are some properties of phase transitions which make these properties, the phase transitions, similar to chemical reactions. So first of all, it's dynamic equilibrium. So in my case, when I have two different phases which are in equilibrium with each other, that doesn't mean that I have fixed amount of matter in each of these phases, because these two phases microscopically exchange molecules. Molecules from gas phase come into the liquid phase and vice versa. And also, well, during the derivation of this law, I have assumed that the number of molecules in the first phase equals plus the number of molecules in the second phase is constant. So I can write that delta N1 equals to minus delta N2. For which reason I was able to obtain this, this condition. In the case of chemical reaction, so if I have a reversible chemical reaction, so the reaction which doesn't go like with some kind of gas being emerging and flowing somewhere else, but if I have some reaction in liquid in which the reaction can have in two different ways, So I can write that, for example, 2a plus 3b equals to, okay, something like 2c. So these are some chemical formulas. A, B, and C are some kind of molecules which interact with each other, and this reaction can go in both ways. So in here it also can have some kind of a dynamic equilibrium established between these two and this. But in this case, instead of this condition for the number of molecules, I need to have some more complicated condition, and that condition should write as follows, that 2Na plus 3NB plus 2NC should be constant. Well, this condition is much more complicated than that. So I can, in here I can get the 2 delta Na plus 3 delta Nb plus 2 delta Nc is 0. And from this condition, and using the very same method of achieving the maximum of entropy in the closed environment, from this I can get the following equilibrium condition. The following equilibrium condition. Let's say 2 delta Na. So it should be something like this. 2 mu A plus 3 mu B should be equal to something like 2 mu C. Otherwise it wouldn't work. So in this case, I would be able to get something like the equilibrium. So in here I had delta N1 equals to minus delta N2. So from that I get this condition. But in here I have a more complicated condition. So in here I would have this condition for the equilibrium. As you see, it's no longer the equality of the chemical potential throughout everywhere of my phase. When the chemical reactions are being involved, then this condition is changed, and well, now it looks slightly more complicated. Now let's consider another case which doesn't have any relationship to chemistry at all. Another case is called photonic gas. Photonic gas. It's a very interesting kind of ideal gas, the gas which is composed out of photons, the particles which move at speed of light. And the problem with the photonic gas is that you cannot control the number of particles. So even if you have a closed volume, photonic gas interacts with side walls, and photons can be absorbed and emitted by the side walls. So that's the problem, because you know, like there are, for example, that surface of the surface of the door, or the door itself, is not a transparent object. So if a photon falls onto the surface of the door, it doesn't penetrate further. It is being somewhere either reflected back to the room or absorbed by the door. And that happens to many different materials. So also, if you have this metal absorbs light. So as you shine somewhere, the light is being either absorbed or transmitted or reflected. But there is this absorption process. So light interacts with matter. And actually, due to this fundamental statement, or this fundamental law, that light actually interacts with matter, you are able to see. Because otherwise, if light doesn't interact with matter, it would not interact with your eye. It would go through your eye and then somewhere else, and the light wouldn't trigger any kind of a chemical reactions in your eye, which would allow you to see something, actually. So light interacts with matter. And for this reason, the number of molecules, number of photons in the closed volume doesn't remain constant. I have no way to control the number of photons in the closed surface. So probably I can invent some kind of ideal mirrors which only reflect but do not absorb, but fundamentally that's impossible. So what happens in this case? When one photon is being absorbed, so let's say I can write that when a photon is being absorbed, so delta n photons. When the photon is being absorbed, what happens to the number of other molecules or electrons or any other particles? The number of other particles doesn't change. So delta NP is arbitrary. So there is no condition for delta NP. At the same time, I need to demand that the entropy of my photons inside this closed surface is maximum. So that would give me the following condition for the equilibrium of photonic gas, mu equals to 0. So when you have the gas of photons, actually chemical potential of photons in the equilibrium is 0. And that means that for any number or for any amount of the equilibrium photonic gas, its Gibbs potential is exactly equal to 0. It might look like that if you have Gibbs potential, yes, you can probably look at this as the kind of a canonical equation of state for photons, and then from this you might try to derive like what you can derive from the equation, canonical equation of state. Thermic and caloric equations of state. But if you write differential for the Gibbs potential, that would give you something like minus S dt plus V dp. Yeah, so if you take some derivatives of the temperature of the pressure, you would get that entropy is 0. And also, let's say volume is 0. Something is really going strange here. So I have derived rigorously that Gibbs potential is 0, but from that I obtained that entropy and volume is 0. Well, why that happens actually, and what it means? So this is something curious. The reason in here why this approach doesn't work anymore is the same as here. So I cannot control the number of molecules or number of photons. In the derivations for the ideal gas, when I have used canonical equation of state to derive something from that, I have assumed, like for example, that I can keep the number of molecules constant. And that allowed me to derive these expressions. But it's no longer valid here. So, and in here I also treated the temperature and pressure are unrelated. Actually, these two quantities for the photonic gas are related. So you cannot consider them as independent variables. So you can only write that actually minus S dt equals to P VdP. So that gives you, for example, the derivative of pressure over the temperature. This should be equal to, let's say, entropy over volume. So that's the only equation I can obtain using this approach for the photonic gas, for example. To get something more, I need to consider the physics of photons. Okay. And more about physics of photons, I think I would send you as a handout on your email. So I can go even further, but I need to introduce something more about physics of photons. But the most interesting part here that the equilibrium condition is mu equals to 0. And also, this is why this chemical potential is called as chemical potential, because it really applies to chemical reactions. Okay. So now let's take a probably, let's say, 10-minute break and then continue with the seminar.